Hi everyone, just a quick note just to let you know we'll be starting the webinar in just a few minutes, just letting a few people to enter the webinar. I think we've got a lot of people joining now. Well, I think we'll start now. So firstly, welcome everyone and many thanks for joining the webinar today, brought to you by Wärtsilä Energy Storage and Optimisation in collaboration with Solar Media. The topic we are going to discuss today is driving energy storage innovation in a dynamic industry. And I'd like to now introduce the speakers to today. So starting from the left to the right, my name's Caroline Wright. I'm in the Strategic Market Development team, managing UK and the rest of AFU. And then we have Neha Sinha, product management from hardware, and Rashira Shah, product management software. Just to take you through the agenda today, we'll be looking to do an introduction piece to cover the UK battery storage energy market, a view on the BESS landscape's opportunities, and then move into technology and cost innovation, and then innovation and value beyond batteries, and then examples of robust and flexible software solutions, and then a summary, and then we will move into a Q&A. And one thing I'd like to just mention is for any of your questions that will come up throughout the seminar, throughout the webinar or towards the end, please add your questions in the Q&A tab, which will be at the bottom of your screen, and we will answer them at the end of the session. So firstly, it'd be great for those of you who are not familiar with Wärtsilä, and to give you a brief overview of the global business. Wärtsilä Energy Storage and Optimisation is a globally recognised energy storage leader, providing energy storage solutions and lifecycle services that are unlocking the way to optimise power systems. We're integrating end-to-end solutions and building resilient and intelligent infrastructure. We have a track record of over 125 systems deployed and a global portfolio exceeding 12.5 gigawatt hours. Here we just want to give you a view of the UK battery storage market. I think we can all sort of see that we have seen an immense level of growth in the UK, which is now materialised into what is a very sophisticated market. Trading strategies have become more complex as operators adapt and adjust to the ever-evolving market. We've seen ancillary services saturate many times, and operators shift to new sources of revenue in balancing intraday, day-ahead and wholesale markets. But we have also seen National Grid launch new services to deliver greater grid stability, and where battery storage systems can provide grid forming to support high levels of renewable generation. Energy storage systems address the intermittency challenges created by the growth in renewable generation, from extended periods of low wind and solar, and where we may see longer duration systems in the future. Battery storage hardware and choice and advanced software are critical components, I think, to underpin the returns in this dynamic market. And this is where I'd now like to hand over to my colleague, Neha and Rashira, who will take you through some exciting elements of how Wärtsilä is approaching our hardware innovation and where software has a critical role to play. Over to you, Neha.
Great, thanks, Caroline. So as Caroline just mentioned, the UK market really reflects what the BESS landscape looks like globally. So we're seeing high demand for utility scale installations, really exemplified by the increasing number of projects in interconnection queues. We know that EV demand is not quite meeting in certain key markets. The planned supply of cells and some of those cell capacity is now shifting to support the BESS market. We've seen lithium carbonate pricing drop since its peak in 2022, and we expect that trend to continue. And we see increased energy consumption predictions globally, fueled in part by AI, which is expected to consume more energy. And we do see that renewables will take an increasingly large percentage of that total global consumption or production. And that'll need to be supported by BESS. And so that's met today with now rapid industry innovation. We see that our cell suppliers globally are releasing steadily higher cell capacities that have improved performance and have improved degradation curves. We see that many players are releasing increased densities of enclosures, and that's to support more dense sites and sites with higher capacities. We see the continued trend toward looking at alternative battery chemistries. There's no one player that's necessarily coming out on top, but we are seeing that these chemistries pose an important role in the future development of the battery industry, especially as we trend toward longer duration storage applications or things that lithium ion really cannot meet. And then we see that policy is really matching that trend and the growth in the market. So for example, last month, the G7 global storage target was announced to be 1,500 gigawatts by 2030. And so that's a really massive push in the direction to grow this industry. And so on the hardware side, we really can't talk about innovation without talking about cost and how each of these elements of our hardware systems play into the overall cost of a BESS site. The biggest portion of that total cost has historically been and continues to be our battery racks that make up about 50 to 70% of a total BESS cost. And what we really want to focus in on here, I mentioned that we have these increasingly higher density and better performance cells that are coming out. We want to shorten the development cycle to bring those to market so that they are available for sites that we are installing in the next 2 years. And then as battery costs decrease, we do see the other elements of total site cost become more relevant. So what the colors represent here on the screen is the proportion of total cost that each of these categories occupy. And so I'll move left to right. So the next one is EPC and balance of plant. There are a ton of things you can impact here with hardware, with lifting, handling, mounting, foundation. But one key opportunity as this industry matures is standardizing the electrical interface between units. So that's between the energy storage units, the inverter, aux power systems. This would be a collaborative effort that we could take on as an industry, but what it could really do is reduce the amount of unique site training required for EPC contractors and really enable a kind of a more rapid release of these systems. The next category is equipment. So here we're talking about the BESS enclosure itself minus the battery racks, the PCS systems, and any of the electrical connections between the units. We're seeing, again, I mentioned the recent trend, which is a shift from smaller modular units to larger, higher density enclosures. And so this comes with a higher per unit cost. Obviously, larger enclosures are going to come at a higher cost, but you have fewer total units at your site. And so it translates to a lower total equipment cost, and it has a significant impact on some of the other soft costs we'll talk about. As we look at the development cycle for battery racks, and when I say short development cycle, really we're seeing about a year development cycle for battery cells, which is kind of unprecedented, but a really exciting time that we're in right now. So something that we are considering with BESS enclosures and how we can modify our equipment to support that kind of a development cycle is understand how to make those systems and the development practices more flexible and rapidly adaptable to the short development cycle. It's a really big challenge, and it's something that we really are honing into when we think about integration. And with that comes the focus on how to make our systems more flexible as a whole. So we've seen a few announcements and trends toward AC block developments, for example, but there are a number of ways that we can consider making these systems more flexible. The next category over is transportation. So this is one of those soft cost areas that really benefit from the fewer total units at site. We've seen a recent trend, Wärtsilä included, of releasing 20-foot containerized solutions. And this gives you really that benefit of standardized transport from shipping through to trucking. So it means you can stack on container ships. You can use standardized equipment to lift and handle units, both at ports and at site. And you can use standardly available trucks and lashing techniques to secure your components. There is kind of a caution here. As we look at higher density cells, we also see higher weight in our enclosures, and there is a cap there, and we're kind of trending toward that cap with the enclosures that we're looking at today. Eventually, at some point, we risk not being able to transport to all ports, and we risk not having trucks readily available for mass deployment of these units. So that's something we really want to think about as we continue to develop these higher density enclosures. And then locality of supply chains. We're seeing supply chains for energy storage really become more global, some of it prompted by volume and some of it prompted by policy. And so obviously that locality trend will impact and hopefully benefit the cost of transportation to our overall systems as we get closer to our key markets. The next category is commissioning. This is another area where standard electrical connections would be really beneficial. The other thing we think about here is accessibility to components that are critical during commissioning. So that's the switch gears and HMIs. We want to make sure that those are readily accessible to enable easy access and therefore decrease commissioning time. And then life cycle. I mean, this really is regarded as a smaller piece of the pie when it comes to kind of ownership costs, but of course, this is really the capex of your system. This is your 20 years that you're operating your system. And so there are a lot of things that we can think about on the hardware side to really impact life cycle. We have the most ability to impact in design aux power. Minimizing aux power is a huge concern for all organizations that are looking to make that as low as possible, knowing that that is a value you do have to pay for throughout the life of your system. And so anything that we can do to minimize that consumption or even internalize that consumption is really important in the early stages. This is also where any components that need to be serviced, replaced, repaired, maintained should be easily accessible and should be as non-complex as possible to decrease service time and therefore increase availability of your system. And that takes us to what can we do beyond cost? So cost incredibly critical and a huge focus when we think about hardware, but we're starting to see these categories pop up as areas of innovation and value that really take us beyond the batteries themselves or the cost of the system. The first category is environmental impact. So there's a global increase in attention to ESG, environmental, societal, social, and governance. And we see that both on policy and at a community level. There are two ways that we can impact environmental concerns from hardware. The first is to decrease the environmental impact of your system while it's in operation. And so this might mean using low global warming potential or GWP refrigerants. And it might also mean eliminating contaminants such as any kind of excess runoff or byproducts of a potential fire safety event. Those are things that we really want to think about when designing our systems. The second area of impact is traceability of raw materials and really ensuring that we're targeting our manufacturing process to understand carbon footprints and to decrease those as much as possible. And that, is a complex process when we have so many elements of the value chain in battery manufacturing, but really is a key element to supporting the low carbon and ESG forward mentality that we're trending toward. The next category is robustness. So this covers kind of a myriad of things, but I've separated out into these three categories. The first one, of course, is fire safety. We've been thinking about and talking about fire safety kind of differently for the last 6 to 8 years. And we've really shifted away from the mentality about fire suppression, really toward today explosion prevention and how to prevent unit-to-unit propagation of fires. So these are supported by global standards or globally adopted standards like NFPA 55, UL 9540A. But we really think in the fire safety space, we need to we need to think beyond the worst case, or beyond the standards to the worst case scenario. And so that might mean large scale fire testing, which we're doing today at Wärtsilä, and many in the industry are kind of looking toward. And that really is mimicking the worst case scenario so that we can plan emergency response accordingly. The second area here is noise mitigation. This is a topic that has come up really more and more in the last 2 years. And this is because we are moving energy storage sites toward more populated areas. And so we need to meet local noise regulations and minimize community impact. And so when we talk about noise, we're talking about the inverter systems and the chiller systems in our battery units. And the goal would, of course, be to create inherently quieter designs. But in absence of that, we are starting to talk about and seeing talk about noise mitigation kits and how we can really manage noise at each of these sites. And the last category in robustness here is environmental extremes. This one is a potentially really exciting area. We see that there are environments that have extreme temperatures, that have high dust and wind, snow load events, high seismic events. And these tend to be areas that don't have a large BESS market yet. I mean, there are some that kind of fall in one or two of these categories, but really approaching maturity of this market also means building out product capability of operating in these environments. And that's something we really want to think about more with our future designs. And the last potential area of innovation and value driving in this industry with hardware is commercial. So bankability is, of course, always important. We need to make sure that we have proven OEMs that are able to both successfully deliver a project and operate it through its lifetime. But there's also the element of risk mitigation here. So we need confidence in a system, and we need to be able to prove risk mitigation for financing purposes. And so as much as we can, we look at how we can show risk mitigation in a lot of the categories I've already talked about: fire safety, ESG, things like that. Policies and regulations are a really interesting thing to continue to pay attention to. This potentially will shape the way that our industry evolves differently in different regions of the world. And we're seeing this already primarily between, say, regions like the European regions and between the US. But hopefully we do see trends that are more in support of storage installation, as I mentioned, with the G7 release. And then finally, system flexibility. So these systems are intended to operate for 20 years, and it is highly likely that we will want to see use case changes at these sites over those years. And that is really a collaborative effort between hardware and software. So on the hardware side, we really want to make sure our systems are as flexible as possible to support those changes. But we cannot do that without the support of software. So with that, I will hand it over to our software product manager, Ruchi.
Hey everyone, thank you all for joining this webinar today. So I'm going to be talking a little bit about why it's really important to have a robust and flexible software solution in these evolving energy storage markets. And I have a couple examples that I want to share with you that are specific to the UK context, but we are really seeing a lot of these trends happening globally. And I'll talk a little bit about that after I talk about some of our UK focused examples. So I think the examples that I'm going to walk through are really designed to show why you need a software suite attached to your battery system, an EMS provider that can be flexible and does have a robust foundational architecture that allows you to then be able to adapt to changing markets very quickly. So the first example I want to talk about is in the UK, the frequency response markets. So in the UK, we see 3 dynamic response services, and they each have a distinct droop curve with different response times. So we see dynamic moderation, dynamic regulation, and dynamic containment. And we have actually met this market need in different ways, depending on our customer requirements. So we have different customers, and they would like us to meet this market need in different ways, and we have a technology that enables us to do that. So one way that we handle this requirement is by essentially enabling our customers to provide us a schedule of droop curves that can then be dynamically changed as needed. So our customers actually provide us a schedule of droop curves. They can be changing, regularly. They can send us that schedule. So we have, say, 24 hours worth of schedule, and then they can also update that schedule as needed. So that's one way that we've met this need. Another way that we've met this need is by stacking the droop curve and responding appropriately. And one thing that we've noted is that as these markets move towards energy storage, we see things, we see issues cropping up that, the market services are not always initially clued into. So, one thing with batteries is that obviously they can respond to these frequency changes very quickly, and that's usually that's usually a key attribute of batteries. But we also see that sometimes faster is not always better, and so we have seen problems around the stability of the frequency around droop curve elbow points, and we initially hit the problem. We talked to a company that accredits these market services, and they said, we were not the only person to have this problem. And so we had to figure out a way to constructively solve the problem. And that's a really important thing that you need to look for in a software provider is someone who is willing to, essentially dig in and get their roll up their shirt sleeves and get dirty and figure out how to solve these problems, because these are complex things that we are seeing batteries trying to solve, and so you do need someone who is willing to think through the complexities here. So my second example is in the case of automatic low frequency demand disconnection. So National Grid released new grid code requirements. And when they release these new grid code requirements, essentially what this is when you are importing, so when you're a battery and you're charging, and say the frequency happens to be below 50, so let's say it's 49.5, you need to essentially slow your charging according to the droop curve. And when this change came out, it led to some confusion in the market. There was some lack of clarity in how to interpret the grid code. And we actually had some batteries that were already certified and marked grid code compliant. And so we needed to retrofit the batteries, which we did, and we got approval on our first try. And then, so in general, I think these two examples point to some key things that we are seeing globally, and we're seeing how markets are evolving globally. So these markets are becoming more dynamic than ever before. So as we see increased penetration of batteries on the grid, I think that we see markets responding, and they're seeing, the unique attributes that batteries bring. They're also seeing, the way that the markets are changing when you have, say, fewer traditional gas generators. You're having fewer traditional spinning turbines. That changes how markets approach, problems related to flexibility and stability. And so we are seeing a lot of changes happening in markets, and you need to be able to be quick to respond to those market changes. We're also seeing a request for increasingly shorter response times, particularly in terms of ancillary services. So, I think it was typical previously that you would have, say, a minute to respond for ancillary services, then we're seeing shorter and shorter response times requested. So, 30 seconds, 1 second, like 250 milliseconds. And we're seeing markets really taking advantage of the fact that batteries can respond quickly and trying to enable batteries to respond as fast as they can in order to stabilize the grid. And then another really interesting thing that we're seeing globally is increased synthetic inertia requirements for batteries. So synthetic inertia is it's a really interesting topic, but essentially inertia has been traditionally performed by conventional generation, right? Like synchronous inertia. And it was conventionally seen that inverter-based resources like batteries could not provide inertia to the grid. And so, when there's a big voltage change or frequency change, or there's a big generator that trips, obviously inertia helps. And so there's a question of, as we move to more inverter-based resources, how do we manage this grid stability issue? And so, I think that about 10, 15 years ago, the idea was that, well, batteries cannot do this. But then the industry came up with the idea that we could mimic the behavior of synchronous generators with software. And so now there have been, hundreds of publications on how to change the inverter controllers to provide synthetic inertia, to mimic that synchronous generator. And so that's introduced a lot of benefits to grids and enabled grid stability in many ways. So I think that we're going to continue to see many innovations in software in order to ensure grid stability as we move away from fossil fuels and towards more renewables and inverter-based resources. And I think that now we'll have Carolyn will kind of help connect the dots in terms of how these markets are evolving globally from both a software and a hardware angle.
That's great. Many thanks, Neha and Ruchira. Yeah, I think I'd definitely say there's some very interesting points there raised, I have to admit. I was gripped. But no, big thanks to you both. And I think it's evident that driving innovation in battery storage is critical to this ever-evolving industry and market. And I think we can see lots of multifaceted layers in terms of innovation, both on the hardware and the software. So I think there's some really interesting points there drawn out by both Neha and Ruchira. And I think on top of that, in doing this, we're constantly driving to meet the customer needs and ensure that these projects can adapt to capitalise on this changing market, the changing requirements, like Ruchira mentioned, in terms of grid code, both now and into the future. So thank you both for that insight. I think now what we can move to is I'd like to open up the floor to our Q&A. I can see quite a few really good questions actually coming in. And I think if I can sort of kick one or two of them off, and we'll take it from there. Great. First question in is, what changes do you anticipate in the next 5 to 10 years within the energy storage market, and what areas of product development and innovation are most critical to support those changes? I think that question is both Neha and Ruchira.
Yeah, so I can start on the hardware side. I think the biggest trend that we expect to see is the trend toward long duration storage. So we're seeing saturation in some markets, not all yet, but in some markets, of the high power, lower duration applications. And we're seeing that trend now toward longer duration. And so we expect that there are some markets globally, again, this isn't going to be applicable to every region, but some markets where we see kind of the 4+, even 8+ hour durations being predominant in, let's call it, about 10 years time. And so as we think about the way that the industry has to shift to support that kind of a complete change in our demand, we're really looking at its core the alternative chemistries that are available. We know that lithium ion is really able to support up to a certain amount, but is not necessarily going to be the predominant technology that is able to support those longer durations. And so there's a ton of effort that's going around industry-wide to identify what exactly that is, but time will tell. I think that's the biggest thing that we're really looking for in, call it 5 to 10 years time frame.
That's great. Yeah. Fantastic. Rashir, is there any points you'd like to add to that question?
Yeah, I definitely think that we're going to see markets continue to evolve as we increase the penetration of energy storage. So Neha mentioned seeing some saturation in certain markets, and we're definitely seeing some of that, particularly in some of the ancillary services. I think that, we may also see some reduction in the essentially the arbitrage value that can be gained from a typical 4-hour energy storage system. As you increase the penetration of energy storage, that enables us essentially to reduce the steepness of the duck curve. But that also, once you reduce the steepness of the duck curve, you do end up essentially smoothing the price arbitrage in a sort of daily pattern. So I do think that eventually we will see some of that. And as Neha says, the focus will be on more on the longer duration energy storage. So I think that, these are continuously dynamic markets, and energy storage is still relatively nascent. So we're continuing to see how things will evolve. But I do think we will continue to see markets saturate, and then new markets pop up as different applications for energy storage are sort of realized.
Yeah, that's great. Yeah, I think that makes sense in terms of also future-proofing the systems as well. Yeah, fantastic. The other question I think you touched on in the webinar, this is a good one next, is how easy is it to update the BESS system with new grid code requirements? How seamless is this, and is there any impact on performance?
Yeah, that's a great question. So obviously it depends on the specifics of a grid code requirement, but I asked our engineers specifically about the ALFDD requirement. And for us, from design, quoting, and QA, that particular grid code update took about 15 to 20 days. Obviously there's like some back and forth, and so that's not necessarily, that's not 15 to 20 calendar days, but I think that again speaks to the robustness of the underlying architecture and why it is important to choose an EMS provider who can adapt relatively rapidly.
Yeah, great answer, thank you. There's another question coming, just not directly linked, but how would you think about augmentation? And then are there any new ideas on how to approach this?
Yeah, absolutely. Augmentation has been and will continue to be kind of one of the biggest challenges in this industry. There are a couple of reasons why. The first one is when we talk about augmentation, we're talking about 5+ years after a project has been deployed. And at the rate that we are seeing technology released in this market and improved and even obsoleted, then we don't expect that the battery cells and the enclosures that are used in the deployment will necessarily be available when we get to augmentation. So that's the first big challenge. The second is that there's a really easy way to be flexible with augmentation, which is AC augmentation. You add additional AC capacity in addition to DC capacity when you do your augmentation. Unfortunately, that just doesn't work in a lot of areas of the world. So where it does work, that's great. But wherever you have interconnection queues and restrictions, you cannot just add additional PCS capacity. And so I can imagine that we're kind of going to trend in two directions with augmentation, and it's something that we're all asking ourselves. So the first is thinking about an augmentation product how we can maintain product lines that are specifically designed to support augmentation, whether that's through backwards compatibility with existing product deployments, or things like DC to DC converters, which allow you to help normalize the voltages between old and new cells. This is pretty expensive to do. This is a whole new product line that an organization would need to maintain for what amounts to about 10%. We augment, at least in our experience, about 10% of initial deployment. And so that volume is a lot lower, but maybe worth doing to guarantee that we will be able to augment these sites in the future. And then the second direction that we could potentially go, and we are seeing in some respects, is oversizing the PCS at beginning of life. And so this is something that we do, or we have seen with AC block products. You cannot just add new AC block units because it is inherently adding new PCS units. And so oversizing the interconnect is a potential direction we can go, but does result in a pretty hefty upfront cost and is not, again, necessarily possible in all regions. So we're seeing directions for augmentation that could go kind of a myriad of ways, but it has been and will continue to be kind of this really important question on how we maintain these sites long-term and maintain capacity long-term while handling a dynamic, ever-evolving technology.
Yeah, no, that's a great point. I think that now leads quite nicely into energy density. You touched on that within with the webinar. Somebody's asked. I think the energy density, I think, to your point as well, has got a good point about future-proofing the system and footprint, obviously, with the value of land and the lease, the cost base. Energy density, getting more megawatt hours onto a smaller footprint is an important thing. But the question that's come in is, what's our forecast? What's your forecast for energy density improvements for the coming years?
Yeah, I mean, there's a little bit of a crystal ball on this, but the announcements that we've seen with energy density increases are kind of radical and pretty impressive. So we're seeing announcements for, just 2 years ago, we were talking about 280 amp hour cells. Now we're seeing announcements for 1,000+ amp hour cells. And so, again, the integration of those systems is something that we're really excited about, but it's also not necessarily a race to the most energy dense system that can possibly exist without considering the other implications like fire risk and like any sort of risk mitigation when it comes to you're putting an incredible amount of density in a single enclosure, and the amount of gas buildup that you could have in a thermal runaway event, or the catastrophic loss that you could have in an emergency event, or the willingness of certain entities to transport such a dense enclosure is something that we're considering there as well. So there is kind of this push to the most dense enclosure possible, and we are seeing that continuing to trend up. There is likely a cap somewhere. I can't, for myself, in my experience, necessarily predict where that cap is, but I do think we're starting to see the cap in what we can then integrate into a singular enclosure.
Yeah, that's great, Neha. Thank you for that. Yeah, another good. There's some great questions coming in here. There was another point, which I think links to the ESG point that you raised. It was as, with the surge of LFP batteries, how do we see the availability of critical minerals, lithium and copper mainly, in the future? And with the introduction of the Critical Mineral Act, what will be the impacts of LFP battery price and availability?
Yeah, so I think this is a really great question, and I will not claim to be a policy expert, so there's definitely more here that I myself will want to learn as well. I believe the Critical Mineral Act is a U.S. bill that is intended to look at the sourcing and processing of raw materials that are used in critical technologies like LFP batteries, and it's really one in a multitude of efforts to take supply and take control of this industry in really outside of China, which is where, of course, we see majority of volume coming from. And so I think that the availability of lithium and copper for LFP batteries is absolutely a question that is at the forefront of everyone's mind, not just for the volume of availability, but for the geopolitics involved in securing that volume. And I do definitely think, I think there was a follow-up to that question, which was, will it help the transition to alternative battery technology faster? And I definitely think it already is prompting a lot more investment in alternative battery research. And so I think we will see that transition faster, and it will be largely prompted on the heels of both policy changes and the investments that are currently being made into academic research on those alternative chemistries.
Yeah, that's a great answer. Thank you, Neha. Yeah, I think it definitely shows where the policy is driving the industry as well across all of the spectrums. Yeah, that's great. Just sort of moving, there's some good subject areas here, so I might bounce through them. I might be able to answer this one. At the early stages of, this next question is, at the early stages of the BESS industry, fully PC wraps were mainstream, then the typical pattern moved to sort of like more separate packages, balance of plant, split out of the equipment. Do you have a feeling that the fully PC wrap approach is coming back, or at least in the UK? I can answer that question if you like, Neha.
Yeah, go for it, Caroline.
Yeah. I think we did see, and we have seen EPC requested. I think going back to the beginning of the webinar, we're in a very sophisticated market now, and I think a lot of customers or investors alike have moved to splitting out the scope. I think to one, look at control the cost, and then others on the other side of it is sort of matured a bit more, well, a lot more maturity in the industry in terms of know-how and managing sort of multi contracts on the construction side of it. So I think that's where we are today. I think with battery storage, never say never, but that's where we are today. Yeah. Another question, I think probably back to you now. You're getting loaded up here with the questions here, which is great. What do we believe in terms of customers' expectations and inverters PCS wise? Do customers expect any specific capabilities from this part of battery storage as energy projects are becoming more complex and bigger in capacity?
Yeah, for sure. And I think actually, Caroline, if you have some insight on this question as well, that would be really helpful. But yeah, I definitely think that we are seeing evolving expectations from PCS units. And a lot of it comes from the compatibility with these larger enclosure sizes. So as we trend to these larger enclosures, the compatibility to inverters to be able to put the maximum number of racks behind a unit or to connect to a higher number of DC inputs is something that customers are really, really paying more attention to. And so a lot of it is not inseparable from the hardware itself, from the BESS hardware itself, because it has to do with the compatibility and the sizing behind each of these inverter units. And then Ruchi, of course, talked about the grid forming capability of inverters, which is incredibly important as we trend more and more into a renewables grid. But then, Caroline, is there anything else that you think you've been seeing?
I'm just thinking there's a good lead in. Some people have added in some really good questions about the grid forming and synthetic inertia. So I think if I could pose these questions to you, Ruchira, I'll start with this one. So how do you provide synthetic inertia or rapid power injection under a high rate of change of frequency? If you're already exporting at a rated power, how do you provide the overload capacity? And what is the overload capacity and duration?
Yeah, great question. So I think what we've seen in the UK market is that synthetic inertia is it's actually a contracted market. And so you would essentially reserve a certain level of capacity in your battery for synthetic inertia. So let's say you were contracted to provide 20 megawatts of synthetic inertia and you had a 100 megawatt battery. You would not bid into other markets over than 100 minus 20, which is 80 megawatts, right? So you would always have that 20 megawatts reserved for inertia, since you have that contractual obligation. So I think, yeah, I mean, that is how, you know, sort of we handle this via markets. And in terms of the overload capability, that is provided by the inverter. So the parameters for how much overload and duration are configured within the inverter based on the hardware capability and any grid modeling studies that you would do.
Yeah, that's a great answer. I think that, yeah, that's covered all points of the question. Thank you, Ruchir. That's fantastic. Let's have a look. We've got a lot of questions coming in. Yeah, here's a good one. What trends are we seeing in alternative chemistry, sort of non-lithium market? Which chemistries stand the best chance of increased adoption? And what are the key challenges from a design point of view?
Yeah, I mean, I think that this is kind of a dealer's choice question because everybody seems to have their own opinion of which chemistry will really win out. I think the one that we've talked the most about for ourselves internally and a lot of the discussions I've seen recently is sodium ion. And the benefit there is that it is a more accessible technology in terms of raw material, and it potentially comes at a lower cost. But we really do see lithium ion as just such a effective technology in terms of performance and in terms of density that we don't really see with sodium ion. And so overcoming that kind of gap with these new technologies, it will need to be compensated by whether it's volume of supply or lower cost, ideally, to be able to win out over lithium ion. So, you know, there are a number of other technologies that are being discussed, things like solid state and such, but the big challenges are really competing on the key metrics of what lithium ion really stands on today, which is density, performance, degradation, and cost. And then there is a key element there too, which is things like sodium ion do have a lower fire safety risk. And so that is, of course, a great direction to go with alternative chemistries and potentially could also drive us in that direction.
Yeah, thank you. That's a great answer. I think the next one might be to you, Ruchir, actually, or both of you. How do you see the BESS plant controls evolving?
Yeah, I mean, I think this sort of hits on the points that you know, I made earlier in terms of, I think that the BESS plant controls will have to increasingly, you know, essentially be able to take into account numerous different types of economic objectives and be able to essentially respond to those different economic objectives simultaneously. So you may be requesting your battery to do 4 or 5 different things, and you will need to be able to stack your response appropriately to you know, to respond. I also think, you know, from an EMS perspective, from an optimization perspective, you know, as again, right now you can adopt a fairly simple strategy and say, you know, I'm only going to participate in one market and I'm just going to stay in that market 24 hours a day, and that's fine. But as these markets start saturating, in order to drive value from the BESS, you're going to need to be able to forecast different prices and then optimize, you know, according to those forecasts and figure out which markets you want to be in more and which markets you want to be in less. So there's a little bit more complexity around the forecasting and optimization than I think we currently need. So I think that essentially you're seeing a drive towards increased complexity.
Yeah, that's a great point. I think that's what we drew out at the beginning of the webinar in terms of the sophistication of the market, complexity, and I think the ability to shift as the market evolves into new or different revenue stacks. Yeah, really good point there. Throwing in a slight curveball to the renewables one. Here's a really interesting question. Have we considered icefall or any other concerns when placing BESS near wind turbines? Can you offer BESS battery storage cubes containers to withstand ice throw risk and impact? Which distance can be considered as a minimal risk, and what protections can we ensure in such a site? That's very specific to renewables.
It is.
Yeah, it's a great
Yeah,
one.
no, that's a great question. And I think, it falls under that category of environmental extremes that I was talking about, which is these conditions that these units might be exposed to that they currently are not in many of our key markets. And so I can't say personally that we have been talking about icefall, especially when it comes to wind turbine sites, but absolutely there are a number of things that we can do to ensure that that impact does not affect the enclosure. We can ensure that there's no sort of penetration potential for icefall. We can ensure that our snow load rating kind of covers the event that we might see with icefall. We might ensure that our chiller systems have fan vents that won't be impeded by that kind of an event. Yeah, a number of things, but it really, that's a great question. I can't say that particular scenario is something that we've talked about in our developments, but absolutely something that will come up more and more, I'm sure, as these units are installed close to wind sites.
Yeah, exactly, because it leads to another good question, which is similar on the similar theme there, Nia. It says, what solutions can we propose for harsh environments? Exactly to the same questions of dust and high temperatures. So, very cold temperatures, obviously, in that scenario, and very high temperatures, which are all things we need to consider.
Yeah, and a lot of it has to do with, making the outer enclosure of the system more robust. So this is, again, something that might fly in the face of, or maybe not fly in the face. We're really just balancing a number of variables here to try to come up with the optimal solution. And so when you look at these higher density enclosures that we've been talking about, they have very little space left over. Your space between the edge of your module and the door is pretty minimal to be able to still stay within those containerized footprints to make transportation easier. And so when we talk about these extreme environments, we're talking about likely adding insulation, adding protections, making potential inlet areas less exposed. And that requires a little bit more space than we really have in these enclosures today. And so it's really not that, all of these are in opposition to each other, but we're really looking to balance each of those. And it may come with specially designed products or even attachment kits that we need to use for enclosures that are going into these harsh environments.
Yeah, great. And I think this leads into another one. This is to do more with, so given the increasing energy capacity and density of the new products being released into the market, what is your view on how the intensity of fires following thermal runaway might increase as a result, e.g. 3 megawatt-hour thermal runaway event versus a 6 megawatt-hour event?
Yeah, definitely. There's a ton of modeling that definitely still needs to be done in this area. And we know that our mentality about fire events and thermal runaway has turned into more of a gas minimization exercise to prevent then gas buildup that will then lead to explosion potential. And so when we talk about these higher density enclosures, the example here being a 6 megawatt enclosure, the potential for gas buildup is so much higher, especially if you have a cell to cell or module to module thermal runaway propagation. And so that is something that we need to model significantly more. That's something I think standards will start to catch up to as well. But the lower, I think it's a LEL, the lower explosion limit that we see with the NFPA 855 standards today will likely still be maintained, and it will likely be much more difficult to maintain with these higher density units.
Yeah, great. Thank you, Neha. Just conscious time, we're getting, the questions are coming in thick and fast, but I think this one might be good for you, Rashir. What are the capabilities of Wärtsilä EMS? How does it do this? Assuming a BESS site is structured as a split BMU site with BESS split in the BMU group, when it needs to provide mandatory grid code obligation services such as reactive power, is there a master EMS which then has EMS subcontrollers for each BMU group? Along the lines of the grid code points you were bringing out before, I think.
Yeah, that gets a little bit into some of our, specifics related to our engineering, and not really sure how much I can talk about that in this forum, unfortunately. So, I think if someone has a specific question, they can probably reach out to us, and we can talk through it in the proper proper context.
Yeah, absolutely. We can get back to whoever asked that question. Absolutely. Great. And I think we're just looking at the time. I think with the last question here, I think could probably go to all of us. In terms of with increasing energy storage capacity and diversification of systems, where do you see the main challenges in terms of operations and maintenance of the BESS systems in the long run?
Yeah, on the hardware side, I think it's everything that we've talked about before, which is really mostly keeping up again with the technology development as it's been progressing currently and as we continue to progress for the foreseeable future. And so the when I think about operation maintenance, we think a lot about, the warranty of these systems, the way that we need to service them, and we need to replace components over its lifetime. And oftentimes a lot of these components, especially when we talk about like chillers, have the need to be potentially repaired, replaced, kind of halfway through the entire life of the system. And so that's always going to be a challenge. But then keeping up with that as technology is evolving and maintaining those kind of product lines will also be a challenge. And then I think really the key here is how these systems will be used in the 20 years time. I'm saying 20 years, that's what we're assuming is potentially the lifetime of a BESS system. And the way that these systems are used is kind of almost still to be foreseen. We know what they're intended for and maybe how they will operate for the first 10 years, but we also know that markets are changing rapidly, and owners will want to change the use case of their systems over time, and that may impact how they're used and therefore how they're maintained and kept up.
That's great. Yeah, thank you. Thank you very much, Neha and Ruchira. I think we're up at time now, but I'd like to say thank you for everyone for joining the webinar, and mostly to Neha and Ruchira for answering all of those questions. There are still a lot to come, so if there's any that we've missed, we will try and get back to you and answer them. And thank you for your time, and have a great Tuesday. Thank you very much. Bye.